Welcome to this deep dive into an IoT pipeline monitoring system. This platform uses smart bolts to track pressure and temperature in real time and trigger fast control strategies that prevent failures using a time series database and an analytics microservice. The system runs predictive analysis to catch critical anomalies before they happen and send preemptive alerts. Everything connects through unified REST and MQTT interfaces, making it easy to manage pipeline integrity and maintain full operational control. Welcome to the smartbolt monitoring dashboard, the visual command center for our pipeline network. Access begins at a secure login page where each user enters their credentials and receives a session token from the account manager. Once authenticated, the user lands on the system overview, a single page that summarizes the health of the entire network. 4 stat cards at the top display the number of active pipelines, the average temperature, the average pressure, and a live count of critical and warning alerts. Below them, 2 trend charts plot the temperature and pressure of every pipeline over time, side by side. Further down, the service status panel shows whether each microservice is healthy, and a recent alerts feed lists the latest anomalies straight from the analytics engine. A sector drop-down at the top lets the user filter the entire view to just the sector they have access to. An admin sees all sectors while an operator only sees their own. The Pipelines tab lets the user zoom in on a single pipeline. After selecting the sector and the pipeline, 4 stat cards show the location, total bolts, total valves, and the last update time. 2 live charts plot the temperature and pressure readings for that pipeline, refreshing every 5 seconds. The Alerts tab is the incident desk. It lists every alert from newest to oldest, each one showing severity, the originating pipeline and bolt, and the value that triggered it. Filters at the top let the user narrow the stream by severity, sector, pipeline, or limit, and 4 stat cards summarize the current critical, warning, info, and total counts. The Analytics tab offers a deeper analysis on a specific pipeline. After picking the pipeline and clicking Generate Analysis, the dashboard pulls statistics from the analytics service average temperature and pressure with standard deviation, a health score, a risk level with the factors that contributed to it, and the anomaly rate per hour. 4 charts below visualize the temperature versus pressure correlation, the distribution of anomaly types, the predictive trend for where the readings are headed, and a sensor activity heat map showing when each bolt was most active. The Control tab is where humans intervene. Operators and admins can open or close individual valves on a pipeline, open or close all valves at once, or trigger a system-wide emergency shutdown that vents every valve to relieve pressure. Viewers are blocked entirely from this tab. Every action goes through a confirmation modal and is logged with the username and reason in the control center. The Users tab is admin only and lists every user with their role, email, and creation date. From here, an admin can create a new account, edit a user's role or sector assignment, or delete an account entirely. The Pipeline Management tab is also admin only and lists every pipeline bundle in the system. From here, an admin can create a new pipeline. Each new pipeline automatically gets 1 bolt and 1 valve attached, so it is ready to receive data right away, and can also edit a pipeline's name, sector, or location, or delete an entire bundle which removes the pipeline along with its bolt and valve in 1 step. Behind the scenes, the dashboard is a thin front end built on Plotly Dash and Flask. It does no business logic of its own. Every value it displays comes from a fresh REST call to one of the 5 backend services: the account manager, the catalog, the time series DB connector, the analytics service, and the control center. The dashboard registers itself with the catalog at startup and sends a heartbeat every 30 seconds. Just like every other service, so it shows up in its own service status panel alongside the rest. Our Telegram bot lets operators monitor the system from their phone without needing the web dashboard. It is completely dynamic, adapting its behavior based on who is logged in and what they are allowed to see. Security starts right at the chat interface. A user logs in by sending a login command with their credentials. The bot hits our Account Manager REST API to verify them, and from there the experience is customized based on the user's tier. An admin account has zero restrictions, monitoring and receiving live alerts from both sectors simultaneously, north and south. One step down, the operator role is localized. Operators get access to only one specific sector, which is assigned by the admin when their account is created. Once they log in, their view is locked into that zone, with no visibility into the other. At the base, we have the viewer account. This is purely for monitoring. To prevent accidental or unauthorized overrides, a viewer is completely blocked from opening or closing valves and cannot trigger an emergency shutdown. The bot will flat out reject any execution commands they try to send. Users control their notification feed using simple subscribe and unsubscribe commands. With the subscription active, the backend handles the routing over MQTT. As the Raspberry Pi nodes update every few seconds, the admin gets a combined stream of all alerts. The operator only sees updates from their assigned sector, and the viewer can safely watch the logs without any risk of altering the system state. Beyond standard threshold warnings for pressure and temperature, the bot also delivers predictive alerts generated by our analytics service to flag anomalies before a threshold is officially crossed. To keep everyone's phone from blowing up during a continuous data spike, we built in a 30-second alert cooldown per pipeline. The catalog is the service registry of the whole system. Every other service, when it starts up, calls the catalog and registers itself by sending its name, host, port, and a health endpoint. The catalog keeps a live list of every service that is currently running, and each service sends a heartbeat to the catalog every 30 seconds. So the catalog knows it is still alive. The catalog also actively probes the health endpoint of every registered service on a schedule and marks them as healthy, unhealthy, or unreachable. Based on the result, this is the data that the dashboard uses to show the service status panel on the Overview tab. The catalog also stores the configuration of the pipelines, which sector each pipeline belongs to, which bolts and valves are attached to it, and what the sensor limits are. When an admin creates a new pipeline from the dashboard, the catalog automatically generates one bolt and one valve and attaches them so the pipeline is ready to receive data right away. The Raspberry Pi services sync from the catalog every 5 seconds, so when a new pipeline appears, the simulation starts publishing data for it without any manual setup. Finally, the catalog shares the internal API key with the account manager and uses it to sync sector ownership when admin creates or deletes users. The account manager is the service that handles authentication and user management for the whole system. When a user logs in from the dashboard or from the Telegram bot, the account manager checks the credentials against the user database and gives back a token that is valid for 24 hours. This token is then used by all the other services to verify who is making the request and what they are allowed to do. The system has 3 roles: admin, who can do everything including creating users and managing pipelines; operator, who can monitor and control the valves but only in the sector that the admin assigned to them; and viewer, who can only see the data but not act on it. Also at startup, the service creates a default admin account so the system is usable right away. For the calls that come from other services and not from a real user, the account manager has a separate internal API key that the analytics service and the catalog share with it. The analytics service uses this key to look up which users belong to which sector when an alert needs to be sent. and the catalog uses it to sync the sector ownership when an admin creates or deletes users. This way, when an alert fires for a pipeline, only the operators assigned to that sector get the notification on Telegram. The message broker is the layer that ties every service in the system together. Behind it runs Mosquito, the standard open-source MQTT broker. Our Python service starts Mosquito at boot. If nothing is already listening on the broker port, our topics follow a fixed path of sector, pipeline, and event type. Measurements go under sectors/sector ID/pipeline/pipeline. ID/measurements, alerts add the anomaly type, valve commands end in commands/valves, and Telegram commands have their own short path. Alongside running the broker, the service also acts as a passive monitor. It joins as its own MQTT client and subscribes to every major topic with the plus wildcard, which matches one level. We use only the plus wildcard, never the hash wildcard, which would match every level below a prefix. It counts messages by topic route and exposes the totals over HTTP on a stats endpoint with uptime and messages per minute. Like every other service, it also registers with the catalog and re-registers every 30 seconds. The time series DB connector acts as the bridge between streaming events on the MQTT bus and persistent storage in InfluxDB v3. It is cloud-based. This microservice connects to InfluxDB v3 using credentials such as URL, token, and organization. In our system, sensor data is generated continuously, firehose style. Storing this in a traditional relational database, like PostgreSQL or MySQL, is inefficient for high-frequency writes and time series queries. The time series DB connector solves this by writing, subscribing to telemetry topics generated by the Raspberry Pis, parsing incoming JSON payloads, SENML format, and batching them into InfluxDB v3. It stores sensor data for each Raspberry Pi in the specific bucket defined in InfluxDB. Reading, exposing a REST API so other services like analytics and the web dashboard can query historical data using SQL queries without needing to talk to InfluxDB directly to fetch the historical data. In this pipeline monitoring project, the facility is geographically divided into two sectors. North sector, simulated by Raspberry Pi, North-South sector, simulated by Raspberry Pi South. When the system is turned on, the North and South microservices start up in parallel and register itself to the catalog microservice. They receive their configuration like the pipelines and bolts from the catalog. Once configured, the microservices begin their main continuous routine, generating data. Every 5 seconds, the Raspberry Pi simulators run mathematical equations to generate realistic physical readings, temperature and pressure, for every bolt on their pipelines. Also, for assess our system under critical situation, we generate spike data based on the probability that is defined in the configuration file in each Raspberry Pi microservices. They wrap this data in SENML format and publish these payloads to distinct MQTT topics. Each Raspberry Pi has its own topic. Simultaneously, they send quick HTTP requests to the catalog microservice to update the current real-time status of their sensors and valves, ensuring the registry is always accurate. Another main task of the Raspberry Pi microservice is to subscribe to the command topic. This topic is unique for each microservice, which comes from the control center when an anomaly is detected through the analytics microservice. As soon as it receives this command, it changes the state of its local valve. After the valve is changed, the Raspberry Pi microservice confirms this transaction and publishes it to the event topic. Inside the Raspberry Pi, the physics engine reacts to the closed or open valve. It simulates a drop in line pressure and temperature over the next few simulation cycles, bringing the pipeline back to a safe baseline state. The analytics microservice turns the raw sensor stream into real-time decisions for the system. When the service starts, it registers with the catalog and pulls down the threshold configuration and pipeline metadata it needs. Once configured, it subscribes to the MQTT topics generated by the Raspberry Pis to detect anomalies. Once an anomaly is detected, the analytics microservice publishes it on the appropriate alerts topic, for example, sectors, sector north, pipelines, N1, alerts, threshold exceeded, via MQTT. Control Center and Telegram bots subscribe to these topics. In order to send the alert via the Telegram bot to the specific user who has access to the sector where the anomaly was detected, it retrieves a chat ID from the account manager via REST. The service calculates the mean standard deviation and interquartile range of a bolt's history. It runs a linear regression over the data points. If the slope is steep, it flags the trend as increasing or rapidly increasing and computes a confidence score using the R-squared formula. Also, it evaluates multiple rules. It checks static thresholds, performs statistical z-score calculations to spot outliers, evaluates rapid rate changes over a 60-second window, detects sensor failures, and identifies unstable patterns. Using the linear trend, the service forecasts the next 5 values. If the math predicts that the temperature will cross the warning line in the next few minutes, it publishes a prediction warning alert to MQTT before the threshold is actually breached. Also, it calculates a health score and risk score. It starts with a base health of 100 and applies penalties for high mean values, instability, and anomaly rates. If the risk level becomes critical, it broadcasts a risk alert to MQTT. Thanks for watching, and that is how the whole system ties together from the sensors to the dashboard. I have left the repository link and documentation in the description below. If you want to check out the source code, drop your questions in the comments.